Manager for Open Ecosystem at Intel Corporation. You can learn all about us at open.intel.com or subscribe to our wonderful podcast at open.intel.com/podcast. A lot more fun topics here. I'm super excited and happy to be here today with Daniel. Hi, Daniel.
Hello, I'm Daniel. I am cloud software development engineer at Intel. Harshad was supposed to be here, but had a conflict. But I'll just be going over the.
That's all right. Fantastic. What's the topic for today?
It is debugging and troubleshooting with hardware performance counters. I know. I think Ravi mentioned it before, but this is a deep dive into this feature that will be part of the m7i and c7i instances. Every VM, even the small ones, will have access to these performance counters.
Very fancy. And these hardware performance counters, are they a new addition to M7i, C7i, or are they in previous generation of instances at AWS as well?
Yeah, so it'll actually be in all the previous ones for VMs before m7i. So like an m6i, it would just be a full socket VM. So that means just some of the larger VMs, right up until you get to a metal instance, or even a metal instance would have access to, of course, all of them. The VM will have access to kind of core only. Metal, you'll have core and uncore PMU. I'll explain what that is in a second. But the
Fantastic.
really exciting thing about the M7i is that all your VMs are going to have them, even the tiny ones.
Excellent. Okay, let's dig into it then. Hardware performance counters sounds very geeky and very exciting.
It is. Yeah. So just kind of a quick overview of what I'm going to do. I'm going to really deep dive into what hardware performance counters are and how you can use them. And I'll give you real world examples of how these are really invaluable. There's just problems you can't solve without these. So it's really a superpower.
And so you use the term PMU. What does the PMU term mean?
Yeah, so hardware performance counters, it's a piece of hardware on your silicon. It's sitting on your chip. You just didn't know about it possibly until this video. The PMU, Performance Monitoring Unit, it's sort of like CPU, but PMU, the monitoring unit. So it's just another acronym for the performance hardware counters. It's specifically the hardware that kind of orchestrates a lot of this. You can think of PMU as this giant octopus with little tentacles going to all the different parts of your microarchitecture. But I usually refer to it as PMU, but hardware performance counters is a very generic name.
So this is really at the hardware level.
Very much. This is built into your CPU. This isn't
Gotcha.
some software.
Yeah.
There's great software ecosystem built around this that we're now getting to expose really with the M7Is and C7Is.
And this goes back to like how Pat Gelsinger talks about software defined, hardware enabled. So these features are in hardware, and now we are exposing a full ecosystem around it.
Yeah, definitely. Okay. So it has the benefit of being hardware, so you really don't have to deal with any overhead in your software because it's offloaded 100% to the hardware. So what exactly is this? I like to split this down. When you're looking at your server, there's a whole lot of parts. There's your CPUs, your cache homing agent. Here, let me just close this. L3 cache, DRAM, other sockets, power, UPI, memory controller. There's a lot going on, but I just wanted to split it up because there's really two categories for this PMU. There's the core, everything up here, and the uncore, which is everything down here inside of a VM. So that's these smaller M7i, C7Is that we're talking about, like a 2XL or something. You only have access to core, which is still invaluable. But once you get to those metal instances, that's when you can do some very detailed analysis using the uncore. So that's another thing to look forward to with the metal instances. Yeah.
That's wonderful, actually. So core and uncore, I guess uncore gives a lot more detailed information, but core gives you enough for you to kind of start digging into the problem.
Very much so. Uncore is useful for anything past kind of that L2 cache. Once you get to the L3, you can still learn some about your L3 in the core, but But if you really want a bunch of those details, or what's going across socket or going to your DRAM, stuff like that, or what your power is looking like, that you'll need Encore for. But you can get a lot of analysis, especially with Sapphire Rapids. They added some new registers, so you can do even more with the core PMUs. And these little orange dots that I put here say this is just where the PMU, it touches all these different parts, and you can kind of think of a little bit of the PMU sitting on each core.
Yeah, and just for the audience, Sapphire Rapids is the 4th gen Xeon from Intel, which is what is used for the 7th gen AWS series. M7i, c7i, r7i. That's sort of the Sapphire Rapids that we're talking about.
Right. Yeah. Thank you.
What kind of hardware metrics are you saying they're exposed here?
Yeah. So this is, you can really start to see what and I'll dig into this a little bit in a little bit, but it exposes hardware metrics. So this is stuff you cannot get from software, such as how much you're missing your cache, an exact count of how many cycles have elapsed, how many instructions have elapsed. And you can start to derive metrics from these very raw events, like cycles per instruction or bytes sent from one socket to another. Yeah.
Wonderful. All right, let's keep going.
Cool. So if you look at just one CPU, and this PMU is hooked into this CPU, and most people, when they think of a CPU, if they're technical, they know there's an L1 cache and an L2 cache, and some people even know that there's sometimes a split of an instruction cache versus a data cache in the L1 or even the L2. And this isn't a specific CPU. This is kind of just a general picture, kind of a simplified CPU that I wanted to draw to kind of explain some of the complexity of hardware performance that you really just can't see without PMUs. Because like when people talk about CPU utilization, sometimes that metric just doesn't accurately describe that your CPU is fully utilized. It could be 100% stalling out, but still show 100% CPU utilization, so there's more complexity. So when we really dig into what a CPU is doing, there's a whole lot going on just on one CPU. And this doesn't even get into hyper-threading of how we might be doing multiple things all on one CPU, calling it multiple CPUs. But this is one physical core. And so you got this L2 cache, which you're using your branch predictor to pull instructions. You're trying to guess what the next instruction is. You build up a queue. You're decoding that. This could be legacy decoders or newer instruction set decoders for like AVX and some of our really cool vectorized instructions. That all gets buffered, and everything up here is in order. And then you start to get to this out of order magic that's going on in the CPU. People might not realize that you can do more than one thing at once in a CPU. You can be executing up to like 5 instructions sometimes just in one cycle. So you can really be parallelizing your work. So this is where you can start to see CPU utilization isn't as easy to calculate as we might sometimes think. You could just have one port being fully utilized and the rest are sitting empty, and it shows 100% CPU utilization. So this is where it gets really important to look into hardware performance counters. So under each of these ports, you get those instructions. They're scheduling to the ports. Ports are holding things like your ALUs or your dividers or that stuff that you learn about in like circuits class and stuff. And you want to keep these fully stuffed. Like you want to have everything feeding into these as much as possible. And then as those instructions retire, you write back through the memory controller, heads out to the L1 cache. The whole beautiful cycle starts over again. And the PMU is sitting over here. And like I said, it's like a little octopus. It's got little lines going to all these different little parts of the CPU. And it's really more complex than I'm showing right now, where there's config registers and MSRs and all sorts of stuff going on. But at a high level, this is kind of what's going on. Yeah.
So I think that's wonderful, because oftentimes you see that your CPU is 100% utilized. You don't know what is causing that 100% utilization. It could be port 0, port 1, memory controller, buffer, whatever, right? But at a high level, you're just seeing 100% utilization. But with PMU, now its tentacles going into all these pieces can start spitting out those micro metrics for you that you can say, oh, I know what is causing this 100%. and let me see if my software is to be blamed. So it kind of becomes like that cycle that you can gives you more information about your software, and you can debug more effectively.
Yeah, 100%. Because like you said, you could show 100% CPU utilization when really you're just saturating port 0 and
Right.
everything else is sitting empty. Whereas realistically, you could be getting 5 times the performance and you just didn't even realize it.
Wonderful.
So,
Wonderful. Okay, let's keep
so,
going.
so let's zoom into, we're going to zoom in even further. So what is this PMU, or hardware performance counter? You can think of it as it's got 2 different parts. It has fixed registers and general purpose ones. And I like to describe these registers as like when you're going into a grocery store or something and they're keeping head count and they're clicking one of those little clicker things to like count foot traffic going in. All it does is it just clicks in increments. And that's really all that these registers are doing. They're just little clickers that increment whenever a hardware event happens, and it kind of counts that. Again, this is a simplified version, but so you will increment every time a cycle happens, or a ref cycle, or instruction is retired, or this TMA slots, which I'll explain in a sec what TMA means. And there's a little MSR machine-specific register that's kind of hooked up to this. So again, this is a simplified version, but then you have these general purpose registers down here, which you can schedule any event you want on there. If you wanted to, you could collect cycles 8 times. There's really no point to do that, but you could collect like L1 misses. You could look at your TLB misses, your L2 misses, decoder, how much each port is being utilized, all kinds of things you can throw in there. And this is just for the core metrics. I haven't even started talking about the uncore again. So there's really a whole lot of value in just these
So
core
who
metrics.
assigns like what goes, the fixed registers, their purpose is clear. Who assigns what goes in the general purpose register? It is by the programmer, it is by the, who does that?
Yeah, so this is software defined. And I'll go into the tools that can do
Okay.
this in a
Right.
second.
All right.
But again, you write to these config registers that then tell it on what hardware event to start incrementing on. And so that's very detailed, but at a high level, you can like use Linux perf
Got it.
to you can say collect L1 misses and
Understood.
something else. And it'll start throwing those in there. And I'll show in a sec, it can get pretty complicated where you actually can collect even more events than you have general purpose registers, which might be a little mind blowing, but this is where multiplexing starts to get in. So what it starts to do is, say you put in too many events, you start scheduling some of these events for the first 10 milliseconds. I'll just throw out a random number. And then you swap it out for the next group of events for the next 10 milliseconds. So they're recording at different times, but you can still, since it's so high granularity, you can still collect pretty accurate measurements, even though they're not all recording at the same time. But this is where you start to get into a problem. If you want to, say, if you're calculating cycles per instruction, you would want cycles and instruction to both be in the same event group so that they get multiplexed in at the same time.
Right.
And this is usually managed by like a kernel driver or built into the kernel. There's third-party drivers that can do this. You can do like a write MSR to configure it yourself if you really want to be that person. But yeah, so this might seem a little overwhelming, but thankfully there's a great open source ecosystem on doing all of this and tools that have already figured out all these optimal groupings for you to calculate all these metrics that might be interesting.
And I think that's the beauty of it, hardware defined, software enabled. So the capabilities are there. How you leverage them is well defined using software in an open source ecosystem. That's fantastic. Okay. I love the animation, though, how they're dancing back and forth.
Yeah, it's what happens. Multiplexing
Yeah.
can be hard to understand, and so I just wanted to make this so people can
It truly shows, as you were saying, 10 milliseconds, you're measuring one, the next 10 milliseconds, you're measuring second. So
Yeah.
you're defining your batches of instructions that need to be measured by the general purpose register.
Yeah, and I'll show what this looks like in perf a second, because it'll show you the percent of time that specific event was actually being collected, and it'll extrapolate it to if it was only collected for this time, but then what would it have kind of looked like approximate if it had been collected for the whole time. So it kind of does that approximation for you. Very nice. But like I said, I'll go into the tooling in a second.
Yeah.
But going back to this chart back here, this might seem overwhelming. All of this, no one wants to be an architect looking at the silicon. You want to write software that runs fast, right? You don't want to have to look at all those details. So thankfully, Intel's done a really great job coming up with a methodology for looking at CPU performance instead of just CPU utilization, 80%. We look at it in terms of this top-down microarchitectural analysis. Might sound intimidating. It's what I called TMA earlier. There was a specific register built into these m7i instances, this TMA slots one. There's a specific register just for this now. That's how seriously we take this methodology of where you can break down hardware, a CPU performance into kind of these categories, the left side being not stalled. So stuff is flowing through this pipeline. You have instructions getting loaded, scheduled, retired. It's great. Stalled is where things can start to look bad. So this is the retiring. Ideally, you would want everything to be retiring, but that's just never going to happen, because while you're retiring, you also need to have a bunch of stuff coming in and being decoded. So it's just impossible to have 100% retiring, but retiring's good. So sometimes people see, oh, I have a whole bunch of retiring, I need to reduce my retiring, but that's not necessarily how it works. And then
because that makes space for new things to come in.
Yeah, it does. But then the other one that also can sometimes confuse people is once you start looking at how your CPU could be stalling, as in there's room for more efficiency, there's the front end bound and the back end bound. And this isn't like JavaScript versus Java, like running in your browser versus on your server. This is front end bound means loading. Back end bounds mean that it's like you're bound based off of how quickly you can feed things into your schedule, and front end bound is like how. So like if you look at this, there's the how quickly can you feed stuff into the scheduler versus how quickly can you push stuff through the scheduler, and that's kind of what you can think of is that breakdown between front end versus back end. So where are you spending that?
At the end of the day, when I look at that architecture, I realize that scheduler could potentially be the bottleneck. And if you can get more detailed data about front-end bound, back-end bound, the more analysis you can get out of that, which was not possible up until now. And now you can get that data. Now you can do some intelligent things around it.
100%. So here you'll see in back-end bound, there's like port 0, port 1 or 2. These were those things I was showing you on the architecture diagram back there, making sure that those are utilized and that there's not a clear bottleneck of maybe you have way too much L3 bound. So everything's just missing your 1 and 2 cache and jumping straight to L3. Or maybe you're really bound by memory bandwidth and you should upgrade your instance to something that has better bandwidth, something like that. So this can be useful for that kind of instance selection as well, to really characterize your software and see this is just how my software is working from a hardware perspective, and which you couldn't have seen before. And once you get that characterization of your software, then you can start looking at the instance selection and saying, I know that my program is memory bound, so I should find an instance that's maybe tuned better for that, or maybe I know that it's frequency or fits really well in the cache, or just things you couldn't have known before. And the great part about all of this that I highlighted over here is that it's low overhead because it's hardware. It's pretty much free. It's not going. Sometimes I've seen logging be the bottleneck in people's software. They don't realize that their loggers are using up like 10% of their CPU or even more. But this is honestly free because it's built into your hardware and it's extremely high granularity. Like some of these operating system statistics, you expect it like once a second or in a good case, or maybe even once a minute. But this you can get to below 10 milliseconds for these events. That's how granular you can get down to literally how many instructions are being retired for every cycle. You just never get that from software.
So even with that granularity, the overhead is extremely low because it's baked into the hardware, and it's upon the developer to be able to use these instructions, because no matter what, if you're using Sapphire Rapids, this is there.
Yeah.
Beautiful.
So there's kind of two different ways you can run it. You can run it in a recording way, which will start to introduce a little bit more overhead. And recording, this is like a perf record, which some people maybe have seen, like Brendan Gregg's flame graphs. If you want to generate a flame graph with hardware events, you would get a little bit more overhead because it does a whole lot more than just read those registers and increment. Every time it reads the register, it'll like sample and do a stack walk and figure out exactly what software is running current instruction pointer and all this other information. But that's honestly just a wrapper around the PMU, which you could also do perf stat, which just runs it in counting mode, which is what I was talking about, where it will just count. And that's honestly like almost 100% free. But even the sampling mode is very, very low. Very low.
Fantastic. All right, that sounds pretty exciting. What do we got for this then?
Yeah. So there's some problems that you can only solve with these PMUs that I keep hinting at. And Netflix actually had a good blog that I'll go through in a second about some work that we were doing with them, where they solved a problem, threefold performance increase that they only really could have done with these performance counters. But I'll just go through a couple of the top things that I keep seeing working with people. So one of the great parts is workload characterization. You can look for hardware bottlenecks to better select what instance you want. So when you're looking at upgrading to those m7i's, c7i's, you might not know which instance you want to pick. And you might even, when you do this characterization, find out that the instance you're on right now might not have even been the best, but you just didn't realize until now. So that's one really useful thing.
So just to break it apart, the m7i, c7i, r7i, each of those instances are memory optimized, compute optimized, IO optimized. So the workload characterization will actually give you details that from the hardware perspective, this is the characterization that you're seeing. So then you can say, oh, you know what? The hardware characterization tells me this needs to be optimized for IO, but I'm using a memory optimized instance. So let me switch it over and run it over there to get a feel for it.
Yeah, 100%. And some other issues that people might not think about when they're picking an instance is, for example, a VM might sit across multiple sockets. And when I say socket, so you have a motherboard, you put two of these chips down to get extra CPUs. And so that's a multiple socket system. But there is a small penalty sometimes going back and forth between those two chips on one motherboard. And people don't realize this when they're deploying in their VMs. I've seen people go from one instance to the next instance because they just think they need more CPUs. But in reality, they start going across this NUMA. NUMA is kind of what we call when you go across that barrier between those two different chips on one motherboard, that across that socket, and you start hitting that penalty. And there's a good way to do that, where you kind of isolate as much as possible to those two different sockets. But there's no way to attribute poor performance to a NUMA penalty without PMUs, because the operating system won't tell you if you're reading from the other one, if you're sending stuff across the sockets, you just can't see that. And another one is false sharing. And this just shows up more and more often as we're getting more and more CPUs out there. Massively multi-threaded programs running on these big systems, and you naturally start to run into kind of parallel issues where different processes aren't necessarily playing nice together. And the list goes on. There's like C states where maybe you're going into too low of C states, or maybe you're not going into low enough of C states to let your other cores turbo. There's just a whole bunch of things that you just can't even start to look at until you have these PMUs. So I'm going to go through a couple specific examples of this, and then I will get to the tools eventually on how you guys can start doing.
Yeah. I would love to see like a demo or something that kind of walks us through these performance counters. But this sounds very exciting, actually, because it truly opening up the venue that was not possible up until now by getting really, really, instead of saying, oh, I'm 100% occupied, let me try a higher memory or a higher compute instance. You're truly giving the information which will allow them to make that right decision for them.
Yeah. Before, a lot of times people would guess, and it's not a bad approach to guess. You just try a whole bunch of different instances and see which one works best. But this time, you actually have the numbers to know. You know what you're bottlenecked by, what's holding you back, and what would best fit for you.
Got it.
So what is this NUMA penalty? This is kind of what I was describing earlier, where you have one motherboard, two chips, and this interconnect between those two chips. So when I say CPU one, I mean like a chip for chip one and chip two. And they're talking, this is all on one server. So you're not going to know that this is your VM unless you know that your VM is too big to fit onto one of these. So it'll start to span to that second one. This was an issue that we saw with one workload where when we were increasing, this is very common again, where we're increasing the queries per second from 100 to 300. And we saw the CPU utilization went from 3%, very easy, light workload, jumped up to 66%. First thought, of course, is I need to go to a bigger VM. I'm running out of space on this system. But in this case, thankfully, we were using hardware performance counters. And so we were looking, and you can see CPI also goes up, and CPI is cycles per instruction. So this is a rough heuristic for how efficiently you are feeding feeding instructions through your CPU. You want to ideally be below 1. That means that you are retiring more than one instruction per cycle. So you have more than one port. If you remember that diagram from earlier, more than one port executing it once.
Right.
And so you want to be below 1. Ideally, you can get down to like 0.2, I believe, on Sapphire Rapids, because there's like 5 ports, I'm pretty sure. And
0.2 would really allow you to have 5 of those instructions concurrently being processed by the scheduler.
Correct. And so what we saw was that actually we went from parallelized execution, basically, to now we're at 3.3 CPI. So we know something is getting bottlenecked. And so we want to look further. CPI is usually where I start with. It's a great starting point. Is my CPU not fully utilized? And so it's 3.3. That means we're going through 3 cycles to execute just one instruction, which is really bad.
Yeah. And so the ideal number is 0.2.
Yeah. So there were cycles where we just weren't even doing anything. So this is, but like I said up here, it shows our CPU utilization is 66. So it's saying, oh, you're doing a bunch, but we find here we're not. So what could be the culprit? So this is when we start to look through all these other metrics, and it's nice to do a side-by-side comparison, see what changes dramatically. And what we saw was changing dramatically was this UPI data transmit bandwidth and backend bound. So backend bound, if you remember from that diagram earlier, that's like how quickly we could load things into our CPU.
Right.
We weren't able to load things into our CPU fast enough to execute it. And so the culprit for that was this UPI. And UPI, if you remember from the earlier diagram, I'm going to jump way back here. So we weren't able to load things in as fast as we wanted. And if you look back here, UPI is this ultra path interconnect, which is that piece of your hardware that's connecting you to the other socket. So that UPI, a whole bunch of data is jumping back and forth between these two CPUs. So an easy way to fix this is you just pin everything as much to its own socket as possible. So we tried just doing like a NUMA CTL to reduce it. And you see this. So we're pinning the processes to each separate socket. And you see UPI drops dramatically. It's way less than it even was at queries per second, 100. CPU utilization with NUMA applied and 300 queries per second goes down to 16%. So we were at 66%. Just telling it not to go back and forth across the socket dropped us down to 16%. So that's like a 50% cost savings right there. We didn't have to upgrade our instance. We didn't have to do anything. And you can see CPI gets back to going more parallelized. We're below.
This is amazing, actually. See, because what we are realizing is even the QPS 100 in the non-NUMA way is like 6 times of 1091 versus 138. That's about 6 times of the NUMA way when we are pinning it to the process. And of course, the QPS 300 NUMA is significantly smaller. So I think you're really getting that valuable metrics information that allows you to play with it.
Yeah. And like I said, debugging this would have just been impossible before these m7i
No,
instances.
and that's, well, that's the topic of this webinar. Hardware
Exactly.
performance debugging.
Yeah.
Yeah,
So
fantastic. No, that is amazing.
you get these free wins basically.
And I think the point that I want to do highlight again is very minimal overhead, because this is baked into the hardware right there itself. You have this information available, just use it.
Yeah, it's sitting there, and thankfully it is very easy to use, and I'll go over that in a sec. But,
All right.
second example, this one's just getting more and more common, like I said, with more like coherent issues with using a bunch of threads. Maybe in order to save money, you are reserving these larger instances and putting multiple workloads on the same instance, or your workload is just using more cores because it's trying to go faster. But false sharing is showing up a lot, and this was the one that we ran into with Netflix, where basically they rolled out a change, saw this weird distribution show up where a third of their instances, and they have a great blog post. I highly recommend that you go read it. Perhaps we can put the link, I don't know, somewhere with this. But essentially, I saw this weird distribution. 2/3 of their stuff was running great. A third of it was bad performance. And they had no idea why. Sometimes it would be great and sometimes it wouldn't be. It seemed almost random. So they looked into, they started using these hardware performance counters. And this time they used vTune. The previous example, this was using PerfSpect, and I'll tell you what those names are in a second. They used vTune to really dig down into, they did it in the sampling mode. So it wasn't counting, it was sampling, still a low overhead, and saw down to, the exact line of code that was causing a CPI rate of 110, which is just insane. If you remember what CPI means, again, cycles per instruction.
0.2.
Yeah. So we should be down at 0.2, but of course it's hard to get there a lot of times with these complex workloads. So for some reason, this was causing their CPI to just be awful. And a lot of times you might have to look at the previous, this is actually the assembly for this code. You can see it all side by side. The assembly for that code. When you're looking at lines of assembly, often when you get these samples, you have to look at the previous one because there's a bit of a skid. But there's a solution to this with a precise event-based sampling, PEBS registers. And those are something that Intel has too. Which might have made this a little better, but you look at the previous one. So something about this was causing awful performance. And when they dug in a little closer, they found out that it was actually a case of false sharing. So what this means is you've got two threads that are not playing nice. They are accidentally basically evicting each other from cache and causing this huge thrash, essentially. And the solution was Java, the JDK just needed to add a little bit more padding into this class struct. And so when you add that padding, then these two threads won't clash on their cache lines. And so everything will fit into cache more nicely, more cleanly, and they won't be evicting each other. And when they rolled out this patch to the JDK, immediately you see the performance flattens back out to exactly what you would be expecting.
This just blows my mind. Just blows
Yeah.
my mind. Like, you see this graph, like, what the heck is happening here? You use vtunes to get the screenshot. It is actually pointing to your assembly code and to your source code. And this visual representation on number 3 is, of course, ours. But once you understand, and most of the time in a debugging situation is what's going wrong. Once you know what's going wrong, then it's at least somewhat easier to fix. So this is just beautiful, actually.
Yeah, it was good.
So Daniel, how can people, and you talked about this are sitting in hardware. You mentioned that people can use these capabilities using software. We heard about PerfSpec, we heard about vtunes. How can people use them, and do you have some demo that you can show us?
Yeah. So I'm going to go through, these are just a handful of the tools. There's more tools, and I don't want to hurt any feelings by not naming every tool. So I'm just going to say there's more tools. There's a lot of tools. Linux Perf is probably the easiest one. Everybody's heard of Linux Perf, and it can count PMUs. PerfSpect is a tool, open source tool maintained by Intel. PMC is open source. Andy Clean, he works for Intel, also another open source tool. A lot of open source here. And PerfSpect is a wrapper basically around Linux Perf. So it just does some of that grouping and event metric stuff for you, so you don't have to worry about optimally multiplexing your events in Perf. So that'll kind of do it for you. PCM, the nice thing about that one is that it's its own kernel module, and I'll show you guys some pictures actually. PMU tools, another wrapper around Perf, but it gives you that entire top TMA breakdown, top-down microarchitectural analysis. It'll give you that full breakdown. PerfSpect gives you some of it, but PMU tools, the top level, will give you all of that. And then VTune Profiler, that's if you want a really polished graphical user interface experience for really digging into your code for that. That one's good. So actually, I'll just jump over into the demo, if that's okay.
Yeah, absolutely. Let's do it.
So here, let me just... Oh, looks like I lost access. Oh, I need to regain access.
Okay.
All right. And then I actually spun up 2 of these instances earlier.
So what you have is 2 EC2 instances. What is the difference between the 2?
Yeah, so here I have, one of them is an m7i 2XL. So this is a very small VM.
Okay.
The other one is an m6 metal, because I just wanted to show you guys what it would look like if you did have the uncore, if you, once those metal instances are released for...
And you said the core ones are available across different instances. The uncore are available from the metal instances.
Correct. Yeah. So all your...
When the M7i or the 7i metal instances are available, it will be available there as well.
Yeah. So all of your m7i, c7is will have these core metrics.
Okay.
So if we just do like a sudo perf stat, there's nothing running on here. Sorry, this was the wrong instance. I need to connect to the other one. So this is super easy way to start using your PMUs, the performance monitoring units. So this, nothing running here, but it'll show you how many cycles were retired, instructions retired, branches, missed branches, slots, that top-down breakdown of... Over here, you can see the metrics from it. So this is how much is retiring, front-end bound, back-end bound. Apparently, an idle CPU is mostly back-end bound. It doesn't really mean much because this is an idle CPU, but here you get those instructions per cycle. This is how many instructions you're getting through your system, a good, easy metric.
Beautiful. And this is everything that we just talked about, front-end bound, back-end bound, instructions per cycle, all of that, retiring. Fantastic.
Yeah. And then here I just already downloaded PerfSpect, and you can do a PerfSpect, and it'll just figure out what PMUs are supported. So here it's just going to tell you that it's not able to collect some C6 events and some energy events, but that's okay. We don't.
So this is a C6. This is a C6 instance.
It is a C6 metal instance.
C6 metal.
So
yeah.
2 sockets, so you could have to worry about the that NUMA penalty that we were talking about earlier.
Right.
Here, let me just cancel this. So we did a collection perf process. I'll just post process this real quick, and what it'll generate is it'll generate these CSVs and this nice HTML that you can look at. And I'll just pull that up over here. I already did a run of this. And so this is kind of a nice graphical view of what that top-down architectural analysis would look like, of maybe a pie chart of where you're spending time in your CPU. This is clearly back-end bound with a split between core and memory. Again, this is an idle system, so very low CPU utilization. CPI, I guess, when you're idle is not too great. And then your operating.
Just to clarify, this is all out of the box.
Yeah. I didn't do anything other than what you just saw. I just ran that. And this is that HTML file.
Beautiful.
Yeah. But you can get this on machine understandable CSVs, like metric count. This is all those same metrics if you want to process it in your Grafana or stuff. And then this is going to show you how many cache misses you had per instruction, L1D, L2, LLC, so that's L3, so all the different levels of cache, how much is going to the other side of your socket. So 60% going to the other side might be reason for concern if this wasn't an idle system. And then the nice thing over here is you can start to do those diffs. Here I preloaded a diff of between an idle system and an actual workload. And so you'll see just changing clearly, a lot more CPU utilization on that. But maybe you would want to look at back-end boundedness or bad speculation. See what stands out.
And you are providing that color coding, like the red, purple, kind of give you an indication that, okay, these are the areas that you're going to watch out for.
Yeah. So blue would be anything that went down. Red would be anything that spiked up.
Right. And something has gone down significantly is a deeper blue, like a more purple kind of a color in that sense.
Yeah. And then if you want information on these metrics, because sometimes they can be hard to understand if you're not, a CPU architect or something, you just mouse over and it'll say the memory latency. This is fraction of cycles where performance was likely hurt due to latency from external memory DRAM. This doesn't aggregate, so it'll just give you those nice little descriptions.
So it is not just meant for CPU architects, but it is actually meant for mere mortals like us who can actually put this information in.
Yeah, 100%.
Fantastic.
The goal is there's a whole bunch of infrastructure around making these very, very user-friendly.
Excellent.
Yeah. So Linux Perf, this is what I showed you guys. PerfSpect, I showed you that. PCM, I didn't load the example but you could run that as well. The nice thing about PCM, this was another open source Intel tool that can use these. This one has its own kernel driver, so it's not built into the Linux kernel, but that has the benefit that you could run this on Windows or OpenBSD, and you can still get all of that hardware goodness. And I'll show you same stuff as like instructions per cycle, L2 miss, L3 miss, all these good metrics and events. And then vTune, there's so much that vTune can do that it would be hard to capture all in it. It would need its own video, but it'll give you that full breakdown as well. And you do a capture and then you put it into your laptop and you open it up in your GUI and you can kind of dig around through it and see, for example, down to what function is L1 bound or DRAM bound. And within that function down to literally the assembly, how many clock ticks you're spending on that instruction. And so very, very detailed analysis, but it gives you a way to kind of explore there and kind of discover your way in through looking at, okay, here's my bottleneck. Let's double click on that. Let's double click a little further and you like kind of dig your way into each problem. So
the information is all available. The tools are all there. It's upon the developers to be able to leverage this information and make the best use out of it.
Yeah.
Fantastic. Is that your last slide, I believe?
Yeah, that was everything.
Oh, beautiful. Okay, so I'm gonna get rid of the slide sharing here. So, this was phenomenal, actually. So I think, what is your recommendation to the developers in that case?
So I guess my recommendation is start using this. It's on your it's on your instances already. So start taking advantage of it and use it to get these, like I said, characterize your workloads and start doing performance optimization. You can optimize your workloads so much more when you can view it from a hardware perspective. It's just a whole nother angle to view your own workloads from.
Wonderful. Thank you. I've been wondering about these hardware performance counters for a while, and you really educated me well. I don't code on a day-to-day basis in my daily life, but I really enjoyed this. And if I was still coding, I could very well imagine me leveraging and digging deep into these performance counters and really making the best use out of them. Thank you very much. I really enjoyed the conversation. I hope you had fun too.
Yeah, thank you.
All right. Thank you. I'm going to close the stream now. Bye, folks.